All right, this is the ballistic pendulum recording. This lab, again, is going to use an online simulator. It's actually pretty simple. You just have to make sure you download the file so you can look at all the equations. All right. Conservation of momentum, conservation of energy, and an equation that you're going to need to use to find the speed after the collision. We applied the conservation momentum on this situation where you have a bullet striking a mass, a target, and then because of the speed of the bullet, it's going to start basically swinging. This mass is attached to a string. You need to know the length of this, which is given here. You can change all these values. At the end of the day, your goal is to find the velocity after the collision. All right? Now, we can do that using conservation of momentum and conservation of energy. The idea is to use both and to do a percentage error. Now, make sure you write down the mass of the projectile, the bullet, the pendulum, and the length. Those are going to be your constants. The velocity of the launcher is going to be given by the software, by the simulator. And you can actually do a few run tests in here, like, you see what happens? It gives you the angle in degrees, and obviously you don't want this to just keep swinging like this. You want to play and then pause, like that. Now, it's going to be harder the greater the speed, so you may want to make this not too much, like that. And then obviously the mass of the target is not as large in comparison with a bullet, so maybe I'll make this 20 grams, or like that. Let's see what happens. Okay, so that's kind of, but that's not enough, so let's reduce this a little bit. Still, maybe I want to put more mass here. Now, sort of, let's put more speed. Okay, that probably makes more sense. There. So what happens in this case, right? The bullet with 81 meters per second strikes the pendulum and they, or the target, and then they both, after the complete inelastic collision, they both go up a certain height. You can find that very easily by using the length of the pendulum. Right? If you know the length of this, which is 2 meters, you can draw a triangle here. And then you can find this length. If you know the angle here, which is 27.9, this will be, let's call it, let's just say 2 cosine of 27.9. Then you can do 2 minus this to find the height. And you need this because in the conservation of energy, the potential energy that the system gains is due to the kinetic energy on the collision, right? So when the masses collide, they both obtain certain velocity. So 1/2 of the total mass, which is the mass of the bullet plus the mass of the target, times v squared equals to the total mass times gravity times height, which is what I show you how to calculate. But clearly the mass is cancelled, and then you can find this. Now, you may be wondering why the equation in the, like, let's show you this. Let's see what is this as well. Why this equation looks like that? Because here, where you have MGH, right? I write down the H as a function of L1 minus cosine. And then the energy, or this V that you obtain here, is the V that I show you in the simulation. This is V naught. Now, what's V naught? V naught is the initial velocity of the bullet. Now, if you were in the lab, the experiment will probably be a bit more interesting because you can actually collect data to find the velocity of the bullet before the collision. Here, we cannot do that. So we give you the speed of the bullet, and what you're going to do is you are going to find the velocity using this equation, and then you're going to compare it by using the conservation of momentum. All right. Basically, in the conservation momentum, you have mass of the ball V naught times M times V. Now you have the mass of the ball, which is the mass of the bullet. You have the total mass, which is the mass of the target plus the mass of the bullet. V naught, you have it, is here, the bullet speed. So you're going to find V. That's basically your theoretical value. Then you are going to find V, this V here, by using the angle from the software. So by using this angle. How? By doing 1/2 total mass V squared equals to mgh, which h was the height I showed you before. But the mass will cancel, so V will be the square root of 2g. What was h? L, which is this, L 1 minus cosine theta. So actually, when you guys open the file, I have to do a correction, I just noticed. This equation is the one that you have to use. And in here, what you guys have in here is the equation for V naught. So I will make sure that's corrected. All right. So when you open the file, it will be updated. Again, the experiment, it becomes very easy because of that. You don't have to worry about V naught because V naught is given in the simulation. All right. Actually, you could do a percentage difference between the theoretical value and this. But this is also theoretical value. So feel free to double check. Feel free to double check. It's not here in the lab. But you can double check the initial speed before the collision using this equation and the one given by the software. All right, to see how accurate it is. Other than that, it's just that. Then you have energy situation, like you want to compute the energy before and after the collision. The energy before is just 1/2 mv squared, which is this speed. So 1/2 mass of the bullet times the speed of the bullet squared. And the energy after the collision will be mgh. So capital M, mass of the ball plus mass of the bullet, times gravity times the height. So again, L times 1 minus cosine theta. I might have to give you the questions here. And then you can find the value Q, which is basically a factor that compares, like gives you a percentage difference, right? Between the energy before and after a collision. And as you know, in a complete inelastic collision, when the target and the bullet, they stick together, the energy will decrease considerably. So you want to check that, all right? You want to answer what the skill represent. I kind of already told you what does it mean, okay? And then you have to write a conclusion about the calculation of those energies, all right? All right, guys. So that's basically it for this lab. It's not very complicated. It's a good final lab. Remember that you can also do the circular motion lab. This semester I added it as an option. So if you go to modules, this is the last lab. But you have the circular motion. Now, circular motion is mostly built for exploration physics, but I did add in the video. So if you guys go to the video here, how you can access an online tool that can allow you to do more than 50% of the lab. All right. We tried this semester to give you the two options because we know students, especially with a math, don't have access to the exploration physics. It doesn't work. So that's why you have noticed during this semester that I have added two different, not procedures, but options for each lab. All right. So make sure that you complete this lab. I believe that the energy labs are actually not that bad. They are probably easier than the first labs that you guys did. So take advantage of that. And if you have any question or if you decide to do the circular motion lab, please feel free to do so because it might help you to get some extra credit for the end of the course. All right. So without further ado, I'll see you guys later. And make sure to send me an email if things were not very clear with the explanation. All right.